Okay, we are ready.
Great, thank you so much. So it is the bottom of the hour, depending on which time zone you're in. Maybe it's 12:30, maybe it's 11:30, or maybe it's some other time. I want to welcome you. My name is Paige Graff, and I'm here with a team of folks broadcasting, in a sense, from the NASA Johnson Space Center in Houston, Texas. We're so glad to have all of you joining us today. We want to take a moment to welcome all our participants from over 47 states, DC, Puerto Rico, and even countries such as Austria, Canada, India, Indonesia, Kenya, and Switzerland. We're so happy to have the educators and students and adult educators on the line. And you really are quite a spectrum of folks, from young elementary students all the way up to adult educators. We're all lifelong learners, or at least we hope you strive to be. So welcome to all of you that are joining us. And if you're joining us in the live stream or archive, welcome to you too. Now, one thing I want to mention is I want to do a shout out to our partners at Infiniscope and Arizona State University, and especially Kirk, who has enabled us to host this webinar through their forum, live stream this webinar so those of you out there can see it and watch it and enjoy the content that's going to be shared by our featured speaker. Now, there is a website for Infiniscope if you want to check out their resources. They've got some great stuff available for educators. Now, I also want to welcome not just our featured speaker, but he's our highlight, but also our event facilitators. We have with us today some additional Mars scientists that can help answer questions that you may have during the session. And again, those questions will go, for those of you on the live Zoom webinar, into that Q&A area. So Joanna Clark, Doug Archer, Eve Berger, and Michael Thorpe, all Mars scientists at the NASA Johnson Space Center, here to interact and help you out during the session. But our main speaker, Justin, we're going to turn things over to him in just a moment. If you're curious about other webinars that we may host, there is our website there for you to be able to check out additional webinars we'll have in the future. Here's just a map of where all of you are. You blue dots on the map have signed up for the live webinar, and the yellow dots, those are some of you that might be joining us with the archive. So that's my introduction, just to say hi and thank you for taking the time out of your day. But now I'm going to turn it over to someone we're so lucky to have, very busy scientist, Justin Simon, who's going to share our Mars Perseverance mission overview and countdown to Mars with all of you. So I'm going to stop my camera. I'm going to stop sharing, and Justin, we'll go over to you. And if you want to introduce yourself and then bring up your slides, I'll confirm we can see it all.
Great. Can you hear me?
Yes, I can.
Awesome. Well, welcome everybody. I'm a planetary scientist, like Paige said, at the NASA Johnson Space Center here in Houston, Texas. And I study extraterrestrial materials, so meteorites and samples that we return from spacecraft. And I do this to understand how rocky planets form. Today, I'm going to discuss the Mars 2020 mission. My role on the mission is a return sample scientist. So I'm basically helping plan where the rover will go and on the surface of Mars, and which samples to collect to maximize the science return of the mission. To study these types of materials, or the study of these types of materials, are really my expertise. And so that's the perspective I will be giving you today in this talk. But before I begin, I really want to point out the fact that the success of the mission really depends on many people working as a team. In fact, there are over 200 scientists from all over the world, and many more engineers and other other team members who have and will make this exploration of Mars possible. So I'm going to bring up my slides right now. And I hope that you can see them.
Yes, we can.
Great. Awesome. Well, this is an image of the launch last year. And again, my name and my role on the mission. So there are a number of reasons we want to study Mars, a rocky planet, a close neighbor. Mars has geologic features similar to Earth. Water once flowed on Mars. And we want to know if Mars could have been once supported ancient life forms, and perhaps if we could live there. So like Earth, Mars is what scientists call an inhabitable planet, or just a habitable planet. Fun fact, scientists now estimate that there are over 300 million habitable planets in our Milky Way galaxy alone. That, remember, there, or maybe not remember, but if you don't know, there are 100 billion galaxies in our universe. So that's a lot of habitable planets. Okay, so there are a lot of planetary objects, planets, and other bodies in our solar system. Does anybody online know how scientists study planetary objects? Take a minute to put your answers in the chat.
So for those of you in the live stream or watching the archive, feel free to discuss this question with those around you. For those of you on the live webinar itself, we'll look for your answers and we'll read some of them out loud. Hopefully, if you put your org or school name first, we might be able to give you a shout out. Otherwise, we'll see what types of answers are coming in and how we do study planetary objects. So as I'm looking at the chat, one of our solar system ambassadors says robots or studying Earth analogs. Upper Darby High School says you can look at the light emitted and see how it shifts. UMD College Park is talking about spectrographs, as well as remote sensing, flyby, orbiters, landers, rover missions. One of our participants has even mentioned that you can use meteorites or even telescopes and satellites. And our Museum of York County says by sending missions to those other worlds, it's themselves. So I'm seeing other great answers like optical and radio telescopes, orbiting spacecraft. So we're getting into some specificity here. Recovered meteorites. Duxbury Senior Center is saying a variety of ways, including spacecraft to orbit, land, as well as observations from Earth. And so we've got a lot of really great answers out there, and some are still coming in, and we'll see what others still come in. But Justin, what do you think of these answers so far? Are they spot on?
Yeah, these are great answers. Actually, maybe you guys should be giving this presentation. Here are the ones I had in mind. So basically, starting from the top, observations from with telescopes from Earth. There are also observations, basically telescopes or other from orbiters. So these are spacecraft. Measurements from robotic landers and rovers. And then, of course, true to my heart, collection and studying of meteorites. And then finally, robotic geologists and humans that go and collect samples and then return them. So obviously, many of you were already aware of some of these ways to do this. Some of you may not know where meteorites come from, so I just thought we'd provide a little bit of background. Basically, these images, these are mostly cartoons, although the lower left in the red dashed box, those are real images of asteroids. But these images are supposed to be an illustrative examples of how we get meteorites. So on the left, many of our meteorites, we call them primitive meteorites, they come from the asteroid belt itself. And when these asteroids bang into each other, they break apart, and some of those objects start to orbit the sun and move closer towards the sun as the sun's gravity pulls it. Some of these meteors impact other planetary bodies. So on the right, I'm showing you a painting by Don Davis, in which he's trying to show how one of these other meteors actually impacts Mars and knocks a chunk of Mars off. And that chunk, which would then also orbit the sun for a while, millions of years, but eventually if it crosses within the gravity well of Earth, it would then be pulled to Earth. So we can get primitive meteorites, and then we can get meteorites from planetary bodies, such as Mars, from a sort of a secondary knockoff.
And Justin, just to interrupt for one quick minute, if you want to hide that little blue bar at the bottom, that will make that go away, and folks, now that's perfect. Excellent. Thank you.
Thank you. I wasn't sure that was showing up. Okay, so meteorites fall all over Earth, and we've had a lot of success of finding them. This series of panels of images are actually showing one of the ways we find them. When you have dark rocks falling on dark stone or mountainous or plants, it's really hard to see them. But when they fall on a type of material that you can see a lot of contrast, in this case, snow, the dark rocks on white ice, we have a lot of success. And so this is one of the main reasons we go hunting for meteorites in Antarctica. So as you can see, even in the summer of Antarctica, there's a lot of snow and ice. So another fun fact, did you know that NASA leads expeditions to Antarctica every year to collect meteorites? Okay, so here are just a couple images showing sort of different types of meteorites. On the left, this image shows an ancient so-called carbonaceous chondrite. It's about 4.5 billion years old. It's made of the oldest dust that has formed in our solar system. And it's from a planetary body, an asteroid, that existed before the solar system's planets formed. So it's older than Earth. The image on the right is actually a meteorite from Mars. The composition of both of these types of meteorites record aspects of how their planetary bodies formed. And so we can learn something about those parent bodies when we study these meteorites when they come to Earth. Obviously, the meteor crater picture from Arizona that I'm showing is an example of a meteor falling to Earth, a very dramatic example. Okay, so here's that Martian meteorite again. If you look carefully, if you look on the left, you can see that it has a dark rind in some places where it hasn't broken off. This is called a fusion crust. It forms as the outside of the meteor was starting to melt as it traveled through Earth's atmosphere. When we cut this in half, or when you cut these meteorites in half, you can look into their interior. So on the right, what I'm showing is the cut surface of that meteorite. And then I'm showing some close-ups. These photographs are just about 3 millimeters across, showing different textures. So these dark spots are distinct from sort of the more massive host or matrix of the rock. And what I'm trying to show is that it's a complicated mixture. This sample is mostly from Mars. It comes from a Martian meteorite, comes from a Martian volcano, but it also has a signature of the Martian soil at the surface that was mixed into the Martian volcanic rock when that volcano was struck by a massive meteor. And through compositional analysis here back on Earth, we actually also see evidence of the meteor itself that knocked off this piece of Mars. And of course, because it was found on Earth, it has some terrestrial or contamination from Earth as well. So the point is that we found many meteorites and we've learned a lot from them, but their travels, their journey to Earth can be pretty rough, and that complicates the geologic record that's contained in each that I'm an expert at trying to understand. So what do we do? Well, if we want to have a more pristine record of the planetary rock or planetary body that we're trying to study, we need to go to those bodies and we need to sample them. And so how do we do this? Well, the main way is that we send missions, space missions, and we've done this before. In the late 60s and the 70s, we went to the moon. Here you can see an Earthrise, so you're looking at the horizon of the moon at our Earth. You can see some large rock outcrops where some astronauts are actually collecting samples. Here is an example of a mission that is currently ongoing. This is a real video of basically the sampling device on a end of a spacecraft that is sampling an asteroid called Bennu. This is a dress rehearsal of the sampling, but it is exactly the same thing that we did in our successful sampling event last October. And of course, this is what we're going to be talking about today. This is these are artist renditions of first the sample collection on Mars, and then the return of those materials back to Earth. It's a three mission, 3-stage Mars sample return campaign. So next, I'm going to introduce the Mars 2020 rover Perseverance and some of the science goals. So this is again a artist rendition showing Perseverance, and I will talk about Perseverance quite a bit later on. So here are the goals bulleted for our mission. The primary ones are to identify past environments capable of supporting life, microbial life. We're looking for signs of possible past microbial life in these so-called habitable environments. We are, like I said, it's a sample return mission. So we'll be collecting rock core and soil samples, and then we'll be storing them on the surface of Mars to be returned. But we also have some technological demonstrations. And so one of the things we'll be doing is producing usable oxygen from the Martian atmosphere, both for astronauts potentially to breathe, but also for a fuel. Okay, so this is a graphic that shows the biological timeline on Earth. And you can see this basically, if you follow this blue arch from left to right, you're going from early to later. And what you can see is that early life on the left was simple, and then life got more complex over billions of years. I'm showing this to point out that on Mars, where about 3.5 billion years ago, there was a dramatic change in climate from inhabitable to hostile. The simple organisms were basically were around that time on Earth, and then the more complex life that existed on Earth was after that. So if Earth is a guide, we don't expect to see the more familiar fossils, leaves, fish, bones, etc., but rather microbial ones. So we actually have some of the types of organisms that we expect here on Earth still today. These are this is an image of a shoreline in Australia. These are so-called modern stromatolites. These are living organisms lying just at the sea level, like I said, in Australia. These lumps of rocks, these are carbonates, are living, similar in a way to coral, or that has built up, for example, in the Great Barrier Reef. But these organisms that build these stromatolites are much less advanced than the small animals that we see building coral reefs. Stromatolites are built by microbes. These are single-celled organisms that grow together, forming a thin carpet. And as the sea level changes, and as the light is covered or blocked by the covering of sand, they will grow through that sand layer. At the end of the day, we don't really know what we're going to see, but we do know where to look because we know the basic needs of life. So the basic needs of life are listed here: water, energy, nutrients, and a livable environment, so reasonable temperature, or at least life that we know it as we know it. And so we can predict where on Mars we are likely to find life in the geologic record as well. So near or in bodies of water, near volcanoes or other heat sources, geothermal heat sources, potentially in partially melted subsurface ices. So again, on Earth, we see these classic fossils, fish and leaves, what have you, that are maybe 650 million years old. And then early on, we see these stromatolites, these microbial biosignatures that are 3.5 billion years. So on Mars, we're looking for evidence of past, when we're looking for evidence of past life, we'll be looking for evidence such as the stromatolites. So these can be both chemical and textural sort of biosignatures. And so I'm just showing you some of those images that we were looking at from fossils on Earth. And I'll tell you again more about the Perseverance rover in a bit, but I just want to emphasize that this rover, the instruments that are on this rover, are designed specifically to detect these signs of ancient life, these chemical and textural biosignatures. We probably won't know for sure whether these rocks contain evidence of life and when we're looking at them with the rover. but we will be able to tell once we bring the samples back to our Earth-based labs. And that's because our Earth-based labs are have the ability to make much higher precision images and measurements. But we will have a really good idea of which samples to pick based on these types of observations that we make on the Martian surface. Okay, next I'd like to talk about how we decided where we should go. So this is an eye chart, but basically it's a spreadsheet that is showing a list of sites on the first column, and then some of the scientific selection criteria at the top. So sort of the characterizable setting, the sort of whether we predicted there would be a habitable environment, whether we think that they could potentially preserve the biosignatures, and then something about the quality of the samples that we might get. And so we had a series of 4 landing sites basically over the last decade, in which people, basically the global planetary community, got together and debated and discussed these various criteria. And each time they sort of down selected. So the beginning, everybody showed up with their preferred places. The second shop in 2015, it was reduced to just over the highest site workshop. We got down to the final 3. And so this is if you can see the rotating Mars globe, you can see the 3, the Jezero crater, the Northeast Sturtis major area, and the Columbus Hills area. And so these are just thumbnails of the 3 choices. Again, Jezero crater, this we will be talking about a bit, is a believed to be a river delta. Choice number 2, the Columbia Hills area in Gusoff crater. This was a really interesting area that we've explored previously, and so we could build upon that. There's evidence of hot springs there. And then the 3rd choice is this area called the Northeast Sturtis area, and there's a lot of volcanic activity there and what have you. So here's another opportunity for you guys to put in the chat your ideas of how or why each of these landing sites might be a good place to go.
Again, excellent question there, Justin. And for those of you folks that are watching the live stream or perhaps watching the archive, discuss these landing sites. All of them are good, but what makes them good? And you can discuss your answers, perhaps pause the recording, and then see what other folks may have said. And in the chat, as again, if you put in your school or org name, we can give you a little shout out if you've got some input. And I'm definitely seeing some input come in. As a matter of fact, there was a high school, Henryville High School, that immediately said all of these sites have evidence of past water. Clark Planetarium also said they have the basic needs of life. We have some solar system ambassadors, which are saying a source of water, a heat source, all of which can be associated with the potential life. Even our solar system ambassador in Puerto Rico says there's a presence of water, which is an indicator of the potential for existence of life. Creekview mentions there's warmth and potential nutrition. Even Chaparral Elementary says because there was liquid that could allow life to bloom, quote unquote. And that was Chaparral Elementary. St. Lawrence Middle and one of their students says that there's evidence of life and rocky terrain, which would be good to collect samples to again check for life. Duxbury Senior Center says, you know, there's the potential in areas like Jezero Crater, especially where they're thinking that potentially there's things buried in these samples or buried in this rocky terrain, which would be good to experiment and look at. AX Benavides says they all have potential biological evidence. And even our solar system ambassador in Illinois says energy source, like those geothermal and hot springs, evidence for water presence. And even one of our groups in Arizona says that whole idea of ice melting, the potential of water. And one of our homeschool groups, Homes United Co-op, says organisms are more likely to live near water. So you're more likely to find evidence of life in existence in these particular areas. And I'll just lastly mention Thompson Middle School, identifying those hot springs, giving you again that environment that you might be looking for. So boy, Justin, I only even read a handful of things that came in, but what do you think of some of these responses?
These are great responses, and so I will discuss these in more detail. I just would like to reveal the winner. So the winner is for the Perseverance landing site is Jezero crater. Probably most of you knew that. You actually cannot see that from this image. The arrow is showing you where it is. This is an elevation map. The warm colors, the reds and oranges, are showing you the highlands, and then the cool colors, the greens and blues, are showing you the lowlands. Viewed in this way, it sort of reminds me of the continents and seafloor of Earth. I'll next talk about this landing site. So here is another sort of more enlarged view of that, similar color scheme. So on the left, of course, is now that map wrapped around a globe, and you can still see this massive impact. This is the Isidis impact basin, which we believe happened about 3.9 billion years ago. And even now, you have a hard time seeing Jezero crater. But again, it's interesting that it's right on the boundary between these highlands, these warm colors, the high relief, and then the lowlands, the blue colors. So I'm going to enlarge this field of view again. So this is essentially an image. These are remote sensing data, a real image of the crater itself. And I just want to talk about some of the details that make this site in particular intriguing to us. So we can call it the anatomy of the crater and its deposit. So you can sort of, if you squint your eye, you can see that it's circular. It's got more, the margin of the crater has more relief on the west side. The ellipse, or the near circle white label there, is where we think we're going to land. That's so-called a landing ellipse. But what we're trying to get you to see in this picture, besides the scale on the left, the lower left, is that's 10 kilometers. So this is about a 50 kilometer, 45 to 50 kilometer diameter crater, still really large. But the key here is that you can see these curving features, these river-looking like features from the left, flowing, if you will, into the crater, breaking through the margin of the crater and forming what appears to be a river delta. And I'll show a close-up of that in a bit. And then you can see on the right, as labeled, an outlet channel where water appears to have breached the edge of the east side of the crater and poured out. So the fact that you have this breaching, this feature on the east showing a channel water may be leaving the channel, implies that the water level had to have built up, sort of like a bathtub. And so that tells us, or we can infer, that this crater probably had an ancient lake, and therefore it had a shoreline. And shorelines are great places well, organisms lived there, right? Water, and also to preserve fossils. So this is another series of images where we've sort of drawn in, digitized, if you will, the same anatomy. Again, you can see the inlets and the outlet, and then a close-up of the delta itself. One of the things that we can do with our spacecraft is we can actually view with spectrometers optical indicators of different minerals. And so I'm overlaying here some colors. These false colors aren't necessarily the colors of the rocks that are on this delta, but they tell us something about the minerals themselves that are in those rocks. And so if you go from left to right, you can see that there's carbonate. So carbonate is what makes up coral, makes up carbonate rocks. That's the kind of green yellow. So this is a marginal carbonate, typical of a lake. Then you can see in the blues, this is, or the purples or blues, depending on where you look or what your eye sees. These are types of clays. These are called spectites, iron magnesium clays. And then we see in red olivine. Those olivine minerals are possibly from a reworking of some volcanic eruptions that may have been eroded and carried in to the crater and deposited. We're not sure. It could have also just fallen on top of the lake and settled to the bottom. That's part of what we're trying to get at. So we already have a good idea of the landforms and some of the mineralogy that we will encounter. This is another view of the edge of the crater. Now, again, this is basically using a telescope, if you will, from a spacecraft or from a remote source. You can see at an angle. This is looking up the delta and up the river valley, if you will, towards the margin of the crater. There's actually a pretty large crater right on top of the delta. It's about a kilometer in size. So just to bring this point home, this is a picture of a river delta in Alaska. And what you can see here, the oranges and the yellow and green, these are microbial life that have caught up in the sand. So hopefully I'll go back. You can see the morphological relationship or similarity between these two geologic features. And then, of course, we can go, and we have looked at the actual life that's teeming in this environment. Okay, so we launched July 30th, 2020, last year. That's why we're March 2020. And we I took some pictures when I was out at JPL of when we were going to launch, and I've modified them. We are now going to land in 9 days. So we land February 18th, and we have plans to have that return sample mission in 2026. So next, I'm going to talk about the rover itself and some of its capabilities. So this is an illustration, a very nice illustration of the rover. I'd just first add that a 7th grader, like many of you probably, Alex, he was actually the one who wrote an essay and won this essay contest, if you will, so that he got to name the rover Perseverance. And so this is pretty high honor. The rover, and I'll talk about this in a lot more detail, but it has a whole bunch of instruments. We call it the payload, 23 cameras. Some of them are used for navigating. Some of them are for actually doing science, targeting science features. Some of them are for landing. This is the second sort of excited named component, the Ingenuity helicopter. It was also named by a member of this community, 11th grader in this case, Vanessa, and she named it Ingenuity. And I'm not going to talk much about the helicopter. It's really a technological experiment, but it would be huge if we could have near surface flying capability to basically investigate where we would want to take the rover, whether there is a dead end, whether there's an exciting feature to look at. As well as for helping human exploration as well. Okay, so this next illustration is showing you one of our new landing techniques. So we are still doing the sky crane landing, which I will show a little video of at the end. But we've added this new capability. It's basically an automated hazard avoidance system. We've never done or used this before, but it's pretty, conceptually, it's pretty straightforward. Basically, if you were imagining that you were flying over the terrain in an airplane and you had a map of the area, you could compare that map to what you see below to make sure to basically identify where you were, and then you could go to the places that are safe. This is all going to be done automated. We couldn't land in this crater or near these exciting geologic features if we didn't have this. So we're pretty excited. The funny or kind of odd thing about this is that because it's automated, we know we're going to land in the ellipse and in the crater, but we don't know where. So we could land far to the east. We could land right near this delta, this delta cliff face that's like about 100 meters high, or there's even a 30% chance we could land on top of the delta. So we actually have a pool, a betting pool, if you will, among the team to guess where we're going to land. Maybe you guys can do that within your own school groups too. Okay, so here is a series of slides that basically get into more of the meat of the rover itself. There are a number of instruments. The head, or what looks like the head of the rover in the middle, is called the mass cam Z. The arm out here has got a lot of the scientific investigation capability, and then you can see these other components. Obviously, we have 6 wheels and what have you. And I'm going to talk about each of these different features next. First, I'm going to talk about the wheels. So on the left, you see the wheels of our previous generation rover, Curiosity, and then on the right, the wheels for the Perseverance rover. This is a new wheel design, but it's actually a big upgrade. Perseverance is going to be the fastest rover to date that we have. It's about 3 times faster than Curiosity. Not particularly fast, mind you, but we really need this speed so that we have enough time to find and collect these samples, which is going to require a lot of efficiency and organization. This is that head, if you will, the mass cam Z. It's a series of instruments actually packed in this head. But the main job of this is to take a really high definition video and images of the surface, sort of both landscape, but also targeting some of the workspace that we will be exploring. This is, if I could be biased here, this is one of my favorite instruments. Don't tell my colleagues at JSC about that because they work on a different one. But this is called the SuperCam. This is actually 2 parts. The top part that's on the head has a laser that fires at the rock, and then it has an imaging device. And so in combination, when you're firing this laser at the rock surface, which then causes a little plume that is characteristic of the rock that the laser is hitting, then the images are taken that allow us to identify the chemical composition of the rock or soils, both their atomic and molecular makeup. Another interesting fun fact is that, and I forgot to mention this, is that there are 2 microphones on the rover. So this is the first time we have a microphone in space or on Mars. And we think we'll actually be able to differentiate between the sounds of the laser hitting different types of rocks. Again, that's really a technological development. We don't know how much science we'll get out of that, but it's an interesting feature. This next component, it's on the arm, on the edge. It's called the Planetary Instrument for X-ray Lithochemistry, or PIXL. Its main job is to make very detailed chemical measurements of the rocks at very small spatial scales, so smaller than millimeter scales. And I'll show you a picture of some of that in a bit. This is the next image on the arm. This is what we call SHERLOC. It's a combination of different instruments that, again, using optical properties to detect fine scale differences among minerals, organic molecules, and potentially biosignatures. Along with this this measuring device is really a second set of cameras. You can think of this as a magnifying glass or a hand lens. You might have known, if you were reading the acronyms, that the first one was SHERLOC, scanning habitable environments with Raman and Luminescence for organics and chemicals, and its hand lens, or its magnifying glass, is Watson. So that comes obviously from Sherlock and Watson, famous detectives. So this little handheld camera device will really work in concert with SHERLOC and other aspects of the payload to take close-up pictures of rock textures. And along with PIXL, this is an example of what we might be able to see. So here is a terrestrial stromatolite, and you can see some of the context, the layering, some of the chemical compositions of the different minerals and elements that are concentrated in these different layers. And we hope, obviously, to be able to see some of this. Obviously, if we run into a stromatolite, we'll be dancing in the streets, but in the different rocks that we explore. So the next series of parts of the payload are more engineering. So this is the radar imaging for Mars subsurface experiment, the RIMFAX. This will allow us to actually, I misspoke, I got a little ahead of myself. This is another scientific instrument. This is basically allowing us to look at the subsurface beneath the rover, sort of penetrating the subsurface with this ground penetrating radar. And so, like we do on Earth, if we can't see the different layers of the rocks below the surface, we can essentially hear their bounce back. And so we can then estimate that bouncing time, sort of like a radar or a dolphin, and reconstruct the three-dimensional features of the subsurface. We have a little weather station called MEDA that's on top of it. This is, again, primarily used to determine things such as wind speed, direction, temperature, humidity. Will be important perhaps to understand in our sampling, are we collecting wet rocks? Can help us understand some of the times in which we want to put away our instruments and sort of protect them if there's going to be a dust storm, these types of things. We also learn a lot about how weather on Mars differs from Earth. And then, so this is getting into the sort of the more technological experiments. So this is MOXIE, which is really a resource utilization experiment. This is, if you remember, I mentioned at the beginning, we had a part of the payload that would allow us to produce oxygen from the atmosphere, from the Martian carbon dioxide atmosphere. And so again, this is not producing a lot of oxygen, but it's really an experiment to show that we can do it. We think we can do it. We can do it on Earth, but this is demonstrating that we can actually do it with the Martian atmosphere. Okay, so here again is that illustration of the Perseverance rover, and I'm going to ask you to enter the answers to this question on the chat. If you were a Mars scientist, which instrument would you be most interested to work with, and why?
Great. So thank you, Justin, you've now everyone gotten an overview of each of these instruments. And for those of you perhaps watching the live stream or the archive, you might pause the video, discuss this as a group, or think about how you might answer this question. For those of you on the line, again, if you want to start with your name, your school name or org name, we can give you a little shout out. And we want to know which one of these are you would you be perhaps most interested to work with, but also the why. So you can't just name an instrument. What about it makes it so interesting to you? So we've got the Museum of York County, which says Mastcam Z because of the stereo and 3D images, which they're very interested in. We've got one of our solar system ambassadors from Texas that says MOXIE, so that we can really look at proving, can you create oxygen from the atmosphere of Mars? We've got Hammond Planetarium at Henry Ford College, which is also interested in MOXIE in terms of the oxygen generation. Creative Montessori School also likes the idea of MOXIE because it represents being able to create breathable oxygen in a currently uninhabitable area. AARP, who's mentioning that they themselves are actually a pilot, but they're most interested in Ingenuity, the helicopter, which I know you didn't talk a whole lot about, but also MOXIE. Now, one of our Planet Astronaut Academies is mentioning that they're interested in the sounds of Mars because that just kind of seems like it would be interesting to listen to and even think about the music or the sounds or composing music with those sounds from Mars. St. Lawrence Middle School and Elementary is mentioning that they'd be most interested in PIXL, the X-ray machine, because you'd be able to look into the planet in a different way. AX Benavides is interested in SHERLOC because of the use of UV to be able to gather information. Washington Elementary in Oklahoma says SHERLOC because of the laser and potentially the sounds. Thompson Middle School also mentioned SHERLOC because It can look at some things perhaps that can help identify the possibility of life. One of our solar system ambassadors is mentioning SHERLOC because of the rock and dust and being able to investigate that. Chaparral Elementary mentions RIMFAX because it's radar and could look underground. And I'll just look at one or two more, including Salado Middle School says MEDA, because it'd be interesting and important to keep Perseverance safe. And I think that's that weather station. So you got to kind of know what kind of weather, so to speak, you're dealing with. Maricopa Public Library in Arizona also agrees. They like the weather station and MEDA, and Blue Forest Homeschool says RIMFAX because they're interested in doing some things associated with perhaps growing plants on Mars. Now there's many, many more responses there, my goodness. But Justin, what do you think of some of these answers and their interests? What do you think?
I think it's fantastic, and you know, obviously, I was showing a little bit of my bias, but I could get behind any one of these. You know, I certainly have some personal investment in the SHERLOC instrument because of some of my close colleagues here at Johnson Space Center. But you know, as I get to know more and more people on the team, they convince me how powerful these various pieces of equipment are and how useful they will be for essentially exploring the surface and collecting those samples that I so dearly want to get back. So I'm going to wrap up with a little bit more about the actual sample collection, and then we'll have some, I think, short time for some more questions. But thanks for your answers. So this is a slide that basically is showing in a cartoonish way how we will both sample and then cache, or basically store, those samples on the surface. And so on the left, you can see a little illustrator or a little cartoon of one of the individual tubes, and just next to it is the core, the rock core that would be inside that tube. Each sample will have its own tube. We're very concerned about contamination or cross-contamination. And then this little dancing dashed line is basically showing us that, or showing you sort of where we're going to land, potentially, and then regions of interest that we're going to explore, and then where we would be dropping the various sample tubes. Very, very cartoonish, but hopefully that demonstrates kind of what we're getting at. So this is an image of the rover before it was all wrapped up from the bottom, and you can see those tubes hanging out underneath. You're going to see in a second how they are manipulated. But again, each sample will get an individual tube, and we have a little bit more than 40. Some of them we are reserving for blanks, or what we call blanks, which are basically to give us a baseline or an idea of what does an uncontaminated tube look like. And then we have, again, about 40 that we can sample with. This is basically a image or a video showing how the tubes are pulled out and repositioned. It's kind of maybe hard to really fully appreciate it without spending a lot of time looking underneath the rover. But just to give you an idea that there has to be an entire other robotic arm underneath that handles in a very exact and reproducible way the moving of the sample, both when it's empty and then when it's into a position where it will then be fitted to the end of the arm where it can drill, and then back into its place where it would get its seal, and then finally into a storing place on the underneath side of the rover itself. So here are some images of coring practice. When we went to JPL about 2 years ago now, we went, and I was not involved with actually the coring, but there's a group of engineers and scientists that were working out all these details. Obviously, they don't want to break off the bits. They want to be able to core at different angles and different types of rocks. And so you can see the sort of the size of these bits are about the size of a test tube. And if you look carefully, you can see all kinds of different holes in these different rocks that where these are rocks from Earth, where they tested the abilities and really performed and perfected the rover's sampling, coring capability. So I would be remiss not to mention that these extraterrestrial samples are curated by NASA. Many of them here at the Johnson Space Center in Houston, but they are studied by scientists all over the world. And so you can, as a professional scientist, request samples, and the Mars samples will be the same for scientific research, whether you're in the US or anywhere else in the world. So they're a real global treasure, not just a national treasure. These are some of my colleagues bringing samples in basically ice chests back from Antarctica. I can't remember how many years ago, and then handling some of them in our lunar curation facilities. So this is a little video to kind of wrap up, to show you how dramatic the landing will be. So hold on. So I still get chills basically every time I see that, partly because I'm nervous. So I'm just going to finish up with a couple additional fun facts, and then we can open it up to Q&A. So one of the things that I mentioned early on is that we had 3 final landing sites. So one fun fact, sort of a well-known secret, is that the third area that we would like to explore is really close to Jezero crater. And so what I'm showing here is several notional rover paths that start in the crater, and then after exploring the delta and the margin of this ancient lake, climbing out of the crater and then going towards this third landing site, the northeast Syrtis area. It may not make it all the way there, but a lot of the exciting terrain is actually not that far from our first one. So this extension of the primary mission is something we're planning on, and this is exciting because it would allow us to extend the exploration and possible sample collection of the mission to essentially include a 2 billion year time span, and that would cover all of the major events that we understand for Mars. So that's a big add-on. Then next slide, and this is hopefully something you guys can relate to. This is Dr. Abigail Freeman. She is a planetary scientist at JPL. What I'm showing here is the rover path of a previous rover mission. This is also a crater exploring mission, the Endeavour crater. But if you look carefully, and it's hard to see, what I'm trying to show here is that when this mission landed, when this rover landed, she was in high school. And then I'm showing the various different stops where she graduated from high school, and then she went to college. Anyways, the point is that by the end of this mission, she was a leader of the mission. She was a project scientist. So that's how long these missions last. And so you guys are really, maybe some of you guys that are really young are still a little too young, but those of you who are certainly in middle school, high school, college, and beyond are certainly of the age that you could, through some professional growth, participate in our current missions to Mars. And that's it. I have some other slides, but I guess I can open it up to Q&A now.
Awesome. And I first of all want to thank you so much, Justin, for all of this amazing information about the Mars Perseverance rover. Now, I realize we're getting close to the bottom of the hour, and some of you may need to depart to go to your next class or to go on and do other things that you have on your schedule for today. But Suzanne has put in the chat a link to a survey that we'd love to get your input as you have time. It should only take you a few moments, and all questions are optional. But as we are at near the bottom of the hour, I also want to take a moment to thank our facilitators and Mars scientists that have been on the line. They have answered at least 77 questions for the folks that have put questions into the Q&A area. And they have also given some input in the chat to some of the responses that have come in during this live Zoom webinar session. So thank you so much to Doug, Joanna, Michael, Eve, am I missing anyone? Kim and Suzanne, who have been monitoring things in the chat there and making sure your answers to questions have been answered up to this point. But now in the last couple of minutes, we're gonna do some additional Q&A, and Justin has actually agreed to stay on the line to answer additional questions. So if you have to depart, thank you again for participating. A special thanks again to Justin, as well as our facilitators for being on the line with us today. And we'll continue for as long as we can keep Justin around, maybe about 15 minutes or so, to answer some additional Q&A. So with that, again, for our facilitators, if you have to go, we totally understand, because now we're going to give the pressure to Justin.
Oh dear. Thank you, everybody.
We've got some great questions that have come in throughout the presentation. So let's get to it. So one of our participants is actually asking, you know, about Jezero crater and this whole idea that it's potentially an ancient lake. When was this, in a sense, sort of discovered or known, or how do we know this?
That's a great question. And for a full answer, it would be like a 3-hour lecture. But there are, this is mostly known from remote sensing work. There's a whole field of planetary scientists who are essentially geologists who study images of planetary surfaces. And I don't know who actually was the first to discover Jezero and name it. Jezero does mean lake, by the way, in a Scandinavian language. I can't remember which one. But the age of it is, and this I could go on a long explanation, but the age of it is constrained because we have a sense of the surface ages in the area. So we know that the impact itself impacted this larger terrain, landscape, and we believe we understand the age of that larger terrain. Now we, in an absolute sense, don't. And that's one of the main reasons we want to bring samples back, so that we can actually use labs like the ones I have that I manage here at the Johnson Space Center, and determine the age, the absolute age of those rocks in that surface. But basically, we do a sort of a relative age game where we look at surfaces that have, effectively it's sort of counting. So we have these surfaces that are beaten up, they have more impacts, and therefore we infer that they have been around for a longer amount of time. Then there are these younger surfaces that not only look like they're on top, but they have fewer meteor impacts on them, fewer and smaller. And so we count the distribution and the size frequency of those surfaces, and we can put them in a relative age. We do this for the surfaces of all of the rocky planets in the solar system. It's a great question, though.
Excellent.
So it's all about superposition.
Absolutely. And I was going to say, you know, for those of you that might be studying some geologic concepts and things like the superposition and aspects that allow that age dating, in a sense, to be done is a great part of looking at and understanding the history of the surface of Mars, at least to a certain point. So Justin, here's another question. We were just looking at the landing on February 18th and how that was going to occur. Do you know what time that might be happening, at least on the 18th, so folks can be aware?
Absolutely. So I'm not sure where the question is coming from, but effectively the time is going to be around 1:30 to 12:30, depending on where you are in most of, I think, our listener group on February 18th in the afternoon. But all of that information is on the website, at the NASA website, probably on a lot of different websites, but certainly on the NASA website. And it will be live streamed. There'll be a NASA TV, which is free. You can just type in NASA TV, and it will be telling you exactly what you will get to know. They're starting, I believe they're starting at 11:30 here in Houston, sort of in the commentary, maybe it's 11:15. And then they will live stream when it gets really exciting. They'll start showing stuff. Now, we didn't talk about it too much, but for the first time, we're actually both recording the video and audio of the landing from the rover itself and from the descent vehicle, sort of looking down to the ground and looking at the descent vehicle. Those images won't be available for days. However, we do have sounds and other more instantaneous information that will tell us basically whether it was successful and where we landed within, say, 10 minutes. So we have that 7-minute delay. It'll take a couple minutes to get those initial sort of confirmations of everybody cheers or everybody hides.
And it's a very exciting time. And that little bit of delay and the series of beeps, in a sense, that they hear to get confirmation of that, once those first images do come down, that will be a very exciting time and a very a sigh of relief for many folks, as Justin alluded to earlier. So very, very, very exciting. And do check out the NASA Live broadcasts that they will have to be able to share what the team is experiencing as they're waiting for all of this to happen. So here's another question, Justin, from Hammond Planetarium at Henry Ford College. Now they're looking at this whole idea of navigation for Perseverance. Will Perseverance be able to do any traversing at night, or does it rely on the sun to do any moving around? Can you talk a little bit about that?
That's a good question, actually one that's a bit outside of my expertise. However, I do know in an operational or a functional way, we do rely on the heat, the warmth of the sun, and the lighting of the sun to do a lot of our work. We can work in the Martian night, but we primarily won't. Again, because it's cold, it's much more energy intensive. It gets extremely cold at night. So again, we can do it some, but it's all about the long distance run. We gotta make sure that we can make it to the next day with our limited resources. And so we every single day is planned, every single step. And so in order for us to get as much as done in each sol or each Martian day, we have to be very conservative with our energy use. And there are some measurements that might be better made at night, and so there may be some exceptions. There are some of the illuminations that are problematic. If you're looking down a hole, for example, and you have sunlight, it can cause shadows. But if we are at night and we're using our own lights, we can direct them just down the borehole. So there are some things that we might try, but in general, it'll be a Martian daytime activity.
And that's a great point in terms of, traversing and driving. Safety is always such an important thing. And as Justin mentioned, everything, it's not like someone sitting there with a joystick moving the rover, so to speak, in real time. Everything is planned, and that information gets sent up to the rover so the rover can execute what the team wants it to do. But safety is so important to be able to ensure the rover doesn't get itself in trouble. Now, Justin, something very near and dear to your interests about collecting samples. So a couple of questions related to collecting the samples came in from one of our solar system ambassadors from Georgia and another individual in terms of how long will Perseverance continue to collect samples, and how will those samples be stored? How is that going to work?
That's an excellent question. And the fact is that we are still working out various paths forward. We have evaluated 3 extended rover paths that provide essentially 1.5 Mars years of exploration in the crater, and then another 2 or 3 Mars years outside of the crater. And so it's a game of trying to maximize the science. And so we have only 42 or 43 samples that we can collect. And so we could collect them all pretty early, or we could wait. We don't know what we're going to encounter. So of course, we're playing this back and forth, this parameterization. It will take us about, this is going to blow your mind. It takes us 10 days for one sample, just doing all the images. That's our plan, at least on average. Just doing all the imaging, positioning, making sure that it's in the safe underbelly, taking a post-imaging image or series of images, making measurements around just to make sure we have all the context. Because the in-situ context, the outcrop context is what we don't have for meteorites. I didn't mention this, but that context is huge. We're going to be traversing over the entirety somewhere in the order of 15 to 25 kilometers, depending on what traverse we take. So in the first, and we're still negotiating the sort of 2, 3, 4 year out plans. That's I'm not sure if I answered the question completely, but that's the timeline for sampling.
And that's amazing to think about, that process and how long it will take. And it actually kind of leads into another question that you may or may not have a whole lot of information on. One of our folks is asking, has the design work started to retrieve the cache samples that Perseverance collected in terms of, the launch vehicle being selected or any kind of sample return? Can you talk a little bit to that?
Yeah, I can, but only a little bit because some of it is proprietary. Let me first answer the second part of the other question that I forgot to mention, which I think is key. The question asked whether or not we were going to leave the cache in one place or more than one place. We plan to have 2 primary caches, or 2 caches, one primary and one secondary, because there is a chance we'll get stuck, the rover, I mean, and we could get stuck someplace where this fetch vehicle, and that's the part of the second question, can't get to, and that would be a disaster. And so we plan to basically collect about half of the samples, maybe plus or minus 3 or 4 samples, all critical to the crater, and we will then cache half of that half someplace that we definitely can get to, and then we'll this is notional, but this is the plan. Then we'll carry a duplicate set of that first cache with us as we continue to explore the margin and the outer area around Jezero. And then we'll have a second cache. And then that second cache, it will have all of the highest priority samples that we had from the first part of the mission and samples from the second part. Now, we probably would collect just that second cache because it has the samples from the crater and those from outside, unless there was some disaster. We got stuck in a sand dune, the rover flipped over a cliff face, something like this. So the second question about the next stage, there's a lot of our European partners are involved with and leading this part. Obviously, this is all international, and we're working it across the ocean, if you will. But they have and their partners have very complete designs of what the fetch vehicle would look like. Actually, it's faster than Perseverance. It's going to run in and pick up all the samples and then carry them over to our launch off of Mars platform. One of the things that I was surprised by is that's going to be done automated as well. So that collection of the cached samples is going to be done by a robot that basically drives over like sort of one of your auto vacuum cleaners in your house and picks them up and carries them off.
So very exciting. It's just hard to believe we're right around the corner, 9 days away before, you know, we really get to see some of this come to fruition. So very exciting. Now, Justin, it is 15 minutes to the top of the hour. Are you able to stay on a little bit more, or I just want to be sensitive to your busy schedule?
I appreciate that. I'm good. If there are other questions, I can answer a few more. My kids are doing remote school and they're quiet, so it's like a...
And kids of all ages, that is, because we still have 118 participants on the line, and that doesn't even count the students that some of these educators may have in their classrooms with them. So, so Sina, as long as you're okay with continuing the live stream, we will ask a few more questions. But Sina, if at any point you need to cut it off and go away, I totally understand that as well. And again, before I go into another question, I can't thank our ASU partners with Infiniscope enough because they have really enabled us to use this forum to share Justin and his knowledge, passion, and information about this upcoming landing. So we are so thankful, especially to Sina Kirk and the ASU team with Infiniscope for hosting this webinar. So Justin, here is a question that I think is quite interesting, and I'll be interested to hear what your answer is to it. So one of our participants wants to know, what will we do if living microbes are found in any of the samples or during the mission?
Wow, yeah. So this was we had a lengthy debate about this a couple of weeks ago. We don't think that's very likely. Because the surface environment today is extremely harsh. And what I mean by that is not just that it's cold and dry, but the cloud protection, the atmospheric protection of Mars today is much less than it was in the past, we believe, and certainly much less than it is on Earth. And so the irradiation from the sun is extreme. So people have done experiments to evaluate whether or not microbes could live in this environment, and it's not very long. Now, that said, there are, of course, samples that we could be retrieving from a significant depth. It only takes, you know, a meter or 5 meters of Earth, if you will, to provide a real nice shield where organisms could live. We have a planetary protection division within NASA, and other space agencies do as well. We have a planetary protection officer. Officer maybe is not the right term, but scientist at JSC, Aaron Redberg, a colleague of mine. And so they have been looking into this. And you know, one of the things that okay, let me answer the question a little bit differently. We probably won't know whether or not we have microbes when we're at the surface of Mars. Microbes are microscopic, they're hard to see, right? And so we have plans in place, both containment plans for the sample return, as well as plans in place once they're brought out of the containment, if you will, into our Earth-based labs. Many of these labs that would be handling these samples with potential biomaterial aren't completely built yet, or completely sort of certified, if you will, at least. But the planning is definitely in place.
Excellent. Thank you so much. And, you know, there's a lot of, you know, interest, and even, and I don't want to get into too much detail, but, you know, one of our participants mentioned the Allen Hills sample that is determined to come from Mars. And there continues to be debate on whether or not even any of the findings within that are evidence of potential life. But do you have any brief thoughts on Allen Hills at all, Justin?
Yeah, so actually, I've had the pleasure to work with the Allen Hills 84001 sample. Actually, it was probably the first Martian meteorite I worked on about 15 years ago or so when I was at UC Berkeley. It has a really remarkable record, not just that might have to do with astrobiology, but just to do with the interior of Mars. It's really a deep crustal, maybe mantle rock, probably a deep crustal rock. It has a lot of interesting chemical signatures that tell us about how Mars itself existed 4 billion years ago. One of my colleagues here at the University of Houston has done quite a bit of work on it to refine the exact age in which it formed. The other interesting thing about the Allen Hills meteorite, which you were getting at, is that it has a near surface history. Many of these meteorites have multiple events in them. And so there's like 6 or 7 layers of carbonate rind grown on the side of it. This is not from the interior of Mars, it's from the surface of Mars. And so we've worked on that. And what's really interesting about that rind, it's a little bit like tree rings. We can look at those layers and this is again in our Earth-based labs, we can work out changes in the atmosphere or at least exchange between the atmosphere and the rock and try to reconstruct that history. And one of the things that we at JSC and one of my former postdoctoral scholars discovered was that sample actually has evidence for exchange with a subsurface ice that may be global, at least regional, which is something that we didn't know before. There's always trying to understand whether there was water on Mars, but water could be liquid water or it could be solid water. There are different forms of it. And so that was another great discovery that we had. In terms of whether or not there's compelling evidence of life in the Allen Hills sample, I think that there are some people who are still intrigued by the textures, but I think that the greater majority of scientists are unconvinced that it contains life or evidence of life. It could, but we really want to have better evidence.
And that's the beauty of science. And for those of you out there of any age, science continues. The more evidence you collect, the more data you collect, the more you can support some of your initial hypotheses or interpretations, or the more you may change them. And so for scientists, data, that the questions never end. And as a matter of fact, the more questions a scientist may pose and even get answers to, the more questions pop up. And so that's the beauty of science.
Could I add one more thing, Paige?
Sure.
So one of the things I didn't mention that I just kind of take for granted is, of course, not every chunk of rock that's knocked off Mars survives. And so the point I'm trying to make here is that if you asked a paleontologist or somebody who studied ancient life what type of sample they would want, it certainly wouldn't be the Allen Hills sample. That's from the deep crust. They want a sediment. They'd want clay. They would want something that formed near the surface. And we can't get, those don't survive through impact very easily and then, flowing through this. Going there and getting a pristine sample is so important. So we will go to the geologic record of Mars where we ought to, based on our understanding of the types of fossils that form on Earth, where we ought to see it. And we will collect samples that are much more likely to retain that record.
And we certainly are in an era of sample science between the OSIRIS-REx samples, our JAXA partners and the Hayabusa 2 samples, and our facilities at the NASA Johnson Space Center, we are the home of all of NASA's astromaterial samples. So you get so much information when you can take those samples, bring them into a lab, study them, and help piece together that story. So very exciting. Well, now, Justin, one of our groups from Missouri, they want to know, in Miss Miller's class, would Perseverance be able to enter a lava tube or any other cavernous area to look for or potentially retrieve samples?
Oh, that's an interesting question. I think the answer to that question would really depend on sort of a risk analysis. We would never do anything close to that at the beginning of the mission. We're not going to go across a sand dune for a majority of the mission because the risk is just too high. We do have, we will be doing a lot of our operating via orbiting spacecraft. So we do have some ability to navigate more difficult terrain more of the time. I don't think that we would ever go any place where we couldn't have a full contact or connectivity with the rover, just because even at the end, the risk would be too high.
And that
we certainly could stick the arm in, and we could certainly look in.
And that's a, you know, it's a great question. Even, you know, perhaps those folks and those students know a little bit about some of these sort of caves or these areas that we also happen to even see on the moon, and exploring any of those. You know, the camera resolution of some of these orbiters at Mars really give us great views of the surface and features that, you know, the team will discuss in terms of where to go, where to investigate. And what will be interesting too is the whole idea of, you know, one scientist might want to do one thing, another scientist might want to do another, and the invigorating, to use a nice term there, scientific debate that those team members will go through will ensure that the mission can be as successful as possible, investigating the areas that are perhaps the richest and safest for scientific return. So it's so very interesting. Now, Justin, we have 5 minutes, and I want to try to get 2 more questions in.
Okay.
And one of them is, you know, which one of our participants put in, which is more worrisome or nerve-wracking to you on the team? Is it the launch or landing, and why?
Oh, it's for sure the landing. You know, we launch a lot of rockets, if you will. Not to say that they all are successful, but NASA is pretty good at launching rockets. But in terms of landing, we only have when I say we, I mean the global community, have a success rate of like 40 or 50%. And this is the most difficult landing ever attempted. We're also, at the same time, probably in the best, not probably, we are certainly in the best position to make this landing, to stick this landing. One of the things that is interesting, I don't know if this was designed, but it's an interesting side note, is that the atmospheric pressure will be higher than normal. It's cyclical. Sometimes it's higher and lower, just like on Earth. The fact that it's higher will actually help us slow down. So that might be to our advantage, but we still are trying to land someplace that no one would ever try to land, and no one has ever tried to land before, because it's, of course, scientifically interesting, but it has so many hazards. I mean, I remember, I've heard this several times from the lead in the landing division, if you will, talking about, you know, there are craters, small craters, you know, kilometer-sized craters, 20 meter craters that if we landed in, we could be stuck in for the duration. And it wouldn't even necessarily mean that the rover was damaged, we just couldn't get out. So, you know, that landing part is harrowing, I think. But so that's
So 9 days from now, we'll all be certainly putting in our good thoughts for the rover and its safe landing on the surface of Mars. Now, one last question, Justin, and we so appreciate your time with us, and for the 89 participants that are still on the line with us as well, we appreciate your time. But we'd be remiss if we didn't ask you this question that's come in both as a pre-question as well as in our Q&A area. And it's about you and this career. Why did you pursue this career? What thoughts do you have for any younger individuals that are thinking about their future career? Any thoughts and advice for them?
Yeah, that's a fantastic question. And I wish I had a straightforward, this is exactly what I did, this is how I got here answer. I don't. And I think that's actually part of the message I would give you, is that I didn't know that this is what I wanted to do. I didn't know that this is something that was even possible, to be fully honest. I thought after I went to college, I was going to study studio art and perhaps some type of ancient language. I wasn't exactly sure what I was going to do, but I started taking some science classes and I got really excited. So I guess my point would be is that I didn't have that kind of plan. I was prepared in terms of my scholarship. I wasn't the top student in high school for sure. I was a good student. But in terms of training, I would say, in maybe rearing kids, I would focus on creativity, critical thinking, and dedication. And I think those are huge. It's the creativity that really, I think, is what has allowed me to be successful in this career. I mean, this has little to do with the mission, but I spent a lot of time developing techniques in the labs that I manage, and I have done things that people haven't done before. And it wasn't because I could follow a recipe. It was because I was creative and was willing to think about how to solve the problem, and I was dedicated. I was stubborn, maybe you could say. So I think hard work, creativity, critical thinking. Again, I got educated through the process, but I didn't even think I was going to be a science major when I went to college.
And that's such a great story, because for everyone out there, you got to dream big, and you have to take on any opportunity that you never know where it's going to lead you. And that passion that I'm sure Justin included in his dedication and hard work and critical thinking and thinking outside the box, that's where you're going to find, new answers to questions you didn't even perhaps know you had, and find a passion that perhaps you can pursue as a career. Because I've said this before, and maybe Justin will agree with this: if you can do what you love, you'll never work a day in your life.
Absolutely. I absolutely agree with you, Paige. And, I have a dream job. Again, I didn't know that this job existed. I wouldn't say I stumbled upon it. I was prepared, and they gave me the opportunity. I took it. But I have a great home team, and I have a great away team, and there's a lot of support there. I don't ever feel like, except when I'm in meetings maybe, but most of the time I don't feel like I'm going to work.
And that's really awesome. So it is the top of the hour. Again, I want to take a moment to thank our ASU partners for streaming this. And I know they're going to cut off that stream here, or they can cut that stream off. But I also want to make sure to thank our participants, those that joined earlier, those that are still on the line, those that may be watching the archive. Thanks for joining us. And a special thanks to our Mars scientists that were helping to answer questions in the Q&A. But most of all, a big thanks to you, Justin, for sharing your knowledge, passion, and what folks can look forward to on February 18th as we have our countdown to landing with the Mars Perseverance rover. So with that, thank you. Any last words, Justin?
Well, I would just say thank you and Suzanne for moderating. You guys do a fantastic job.
Well, thank you so much. And we've got great scientists to work with, and we're so happy to have been able to share Justin and our other folks with all of you. So with that, thank you so much again, everyone. We hope we got to most of your questions. We apologize if we didn't. We did our best. Enjoy the rest of your week and go Perseverance.